so I'm going to try to make my talk complementary with Thibault's and look at the problem of motion as it applied to gravitational waves, but I'm trying to link it in with Einstein since he's the main occasion of our getting together. And the particular way that I decided to do that was to look at the question of whether gravitational waves carry energy. That was one of the things that Einstein and more particularly his assistants were worried about, and one of the ways in which the problem of motion was seen as being an attack on precisely that question. And I suppose Thibault had a good quote from Laplace, or from Eddington, in fact, to the effect that once you turn the question around, if you begin by saying, well, I have a system and it's emitting gravitational waves, I expect the gravitational waves will carry away energy, and so I expect that the system will be damped. And so therefore, I expect to have some energy carried away and the system will lose energy. If you look at it, however, turning it around the other way, as a question from within the problem of motion, it's no longer quite so obvious that the system will be damped. Right? When you're looking at it from that perspective, you're not even sure that you're going to get the same sign. And so that's, we'll see that as we go along. So let's start with Einstein. Here's Einstein responding to a gravitational wave. And he did invent the subject. He didn't invent the word, of course. The subject was a little bit in the air in the decade preceding when Einstein first addressed gravitational waves in 1916, almost immediately after coming up with the final form of his field equations. But nevertheless, it was really, in another way, that he did invent the subject because the earlier ideas were relatively vague and incoherent. It's a small point that I won't go into much, that he kept making mistakes of one kind or another, both major and minor. After all, it was a new subject, he was inventing it. Perhaps it's not surprising that his footing wasn't very sure. And one lasting legacy, not his only lasting legacy, was a certain amount of skepticism about it, and perhaps that's natural if you are finding your way, making a few mistakes here and there that you're not exactly sure that you really are on solid ground. So skepticism, I mean, of whether the gravitational waves exist, whether they really carry energy, and so on. And indeed, as you'll see in a minute, he did even ask the question, well, I've introduced them into my theory, but do they really exist? Are they really the condition of the theory? And even when he then seemed to finally settle on the idea that they were an aspect of his theory, we do find him asking if binary stars should emit them. And of course, that's the key question that I sort of alluded to a moment ago. Obviously, the key question is to ask what kind of source do you expect for gravitational waves, and a natural source would be binary stars. So if we are interested in the question of energy, then the question is, do binary stars specifically lose energy as they emit gravitational waves in response to their own motion? If I'm going to talk about the question of energy and gravitational waves, then it's natural to ask how, from the theoretical point of view, you measure the energy content of the gravitational waves. And Einstein addressed that problem right at the beginning of his work by introducing the pseudo-tensor, the energy momentum pseudo-tensor. And that was already very controversial right at the beginning. I've put up a picture here of Tullio de Civita, who was one of those who was strongly critical of Einstein's use of the pseudo-tensor, because of course it's a non-invariant quantity. So if you change your coordinate system, there does seem to be the risk that you're making the energy disappear or come back. And there was quite a considerable controversy in the very first few years of general relativity, not just the subject. I won't have time to go into it, but it was, in that sense, an inauspicious beginning. Of course, Einstein had his arguments saying, well, it's necessary that it be non-invariant because of the way the quality of the gravitational field energy has, if you look at it from the point of view of the equivalence principle. But nevertheless, it was from the beginning already a very controversial subject. But I'm going to skip lightly over the early history of Einstein's going back and forth a little bit on gravitational waves to give you the best idea of where his skepticism originated. In 1936, working with his assistant Nathan Rosen, Einstein looked for an exact solution in the field equations of general relativity. His previous work had been in the linearized approximation for describing gravitational waves. And he ended up submitting a paper with Rosen to the Physical Review called Do Gravitational Waves Exist? And the answer was no. They thought they had uncovered an argument which showed that you couldn't have an exact solution. And when he sent the paper into the Physical Review, he'd only published there twice before. He only started publishing with them when he was working with Rosen. So previously they had published their famous NPR paper and the famous Einstein-Rosen bridge paper. This was the third paper they had sent in. And they got a letter back together with a 10-page referee's report, which was quite critical of the paper and challenged the main conclusion. And so if you're looking for any tips or advice as to how to write to your editor, this letter is one way to do it. So I'll translate. So, my dear sir, we, Mr. Rosen and I, had sent you our paper for publication and had not authorized you to show it to anyone else. And about the, in any case, erroneous remarks of your anonymous expert, I prefer not to comment, and on the basis of this incident, I prefer to publish the paper elsewhere. Now, as I'll discuss only briefly today, it turns out that the referee was right all the time, as Einstein himself a few months later came to acknowledge. So the editors of the Physical Review actually are always delighted when I give this talk. I'm not going to talk too much about this today because it seems to have a good moral from their point of view, which is that you should listen to your referee. Although I have to say that I can remember giving this talk before a room full of physicists, and one of them, after I read out this letter, turned to the others and said, wouldn't you love to write a letter like that? So maybe they weren't drawing quite the moral that somebody would like to do. Obviously, there's a question, who wrote the referee's report? That's a very interesting story. I'm just going to give you the answer. It was Howard Percy Robertson. He was actually a colleague of Einstein's at Princeton at the time, but he was on sabbatical at Caltech when he was asked to be the referee. By the time he returned to Princeton, he had learned, I guess, that Einstein was not very happy with his referee, so he never told Einstein that he was the referee. But luckily, Einstein had now got a new assistant, Leopold Infeld, and Infeld and Robertson quite quickly struck up a friendship with each other. And Infeld had been persuaded by Einstein that his argument was correct, and had come up with his own version of the argument. And in his autobiography, Infeld tells us that one day he mentioned this to Robertson, and Robertson said, well, tell me about this argument. So Infeld said, well, I wrote it all on the board for him. And in his autobiography, Infeld rather touchingly says, and then I was astonished, because right there, spontaneously, he was able to spot the flaw in my argument, not realizing that a few months before, Robertson had been going over this very, very carefully. As he put it in his letter to Tate, the editor of the Physical Review, for the sake of my soul, obviously he was a little worried, as he put it, being the referee for, as he put it, your most distinguished contributor to the Physical Review. Through Infeld, Robertson actually managed to persuade Einstein that he was, in fact, incorrect. And incidentally, Einstein had been in the process, we now know, thanks to Christoph Lehner, who uncovered a draft of a paper that Einstein was writing as a follow-up based on the subsequently withdrawn version of the Einstein-Rosen paper. He had been in the middle of all this, thought he had uncovered something very interesting, and now had to retract it all. And while the paper was improved, come up with a completely new version, which is the version that we know on gravitational waves. Oh, yes, the paper that he was writing. So he was going. He thought, so this is interesting because it looks like things that we would expect to be exact solutions of the theory based on our knowledge of the approximate version of general relativity may not turn out to have exact solutions. So if I recall correctly, the new paper said, let's look at a simple rotating spacetime. Maybe it will turn out that that's not such an obvious exact solution at all. And if we have a clue as to why he was so interested in this, it may be because this was the height of his idea that the general relativistic theory would somehow give a clue to the quantum, that exact solutions would not be the kind of continuous solutions that we were used to in classical theory. So that's the best guess. Okay, so what I want to do is look. We don't know actually what was the exact wording used in the paper that was withdrawn, but we do have the published paper from 1936, Einstein and Rosen. And what's interesting is that even though he now has an exact solution describing cylindrical gravitational waves, he still takes a moment in the midst of the paper to say, well, but maybe it's not so obvious that binary stars should emit gravitational waves. So if I can quote that. Towards the end of the first part of the paper, where he's still dealing with the approximate solution in gravitational waves, he says, it has been concluded that a system in sending out gravitational waves must send out energy which reacts by damping the motion. Nevertheless, if there is present a second concentric wave field, which is propagating inward, this leads to an undamped mechanical process embedded in a system of standing waves. So what he was proposing here was the idea that, well, okay, it's all very well to say that the motion should be damped because you have outgoing waves. That's represented by a retarded solution of the field equations. But if you have an advanced solution of the field equations, then you have waves coming in that are bringing energy. And if you adopt as your solution a linear combination of these two solutions with equal strength, then what you have is gravitational waves, yes, but no damping of the source. And I draw attention to this because it was seized upon by some of Einstein's assistants. But let me first of all make sure that I don't give you the impression that there's any reason to think that Einstein himself was proposing that this was a likely solution in the full case, because if you look at his last words in the whole paper, and these are the last words that he had to say on the subject of gravitational waves, he says at the very end of the same paper, progressive waves therefore produce a secular change in the metric. This is related to the fact that the waves transport energy, which is bound up with the systemic change in time of the gravitating mass of the origin. So that's a nice clear statement that he expects that the system does lose energy and does transmit gravitational waves which carry energy away from the source. But nevertheless, something about that earlier statement passed into the thinking, especially of Leopold Infeld, the assistant that I just mentioned, after the war, and to a considerable extent also into the thinking of Nathan Rosen. So that in the post-war period, you had this considerable debate about whether binary star systems should in fact radiate gravitational waves at all, and whether, or at least in the sense that they are damped in their motion. To give you an idea of where Einstein was coming from with the first quote that I gave you just now, he was thinking back to work that was done early in the 20th century by people like Walter Ritz, with whom Einstein in fact co-authored a short note on this topic, and the Dutch physicist Ted Rode. I quote here Ted Rode, "The sun would not shine if it were alone in the universe." So the idea, which was later embodied in the Wheeler-Feynman absorber theory, that somehow or other the natural solution is in fact a half advanced plus half retarded solution. And if that solution is broken down in any way, it's only because of the fact that we have a large number of absorbers and receivers scattered throughout the universe, and that their back reaction somehow breaks down the original source. As a matter of fact, Rosen was disappointed at some level that the paper that they had written together in 1936 was withdrawn. Incidentally, the reason that he knew that the paper was withdrawn, he had by then gone to the Soviet Union to take the position. The reason that he knew that it was withdrawn was that he read in the newspaper that the paper had appeared. So you know that you're working with a famous person if every slight little paper that you publish gets a notice in the newspaper. So in 1975, Rosen finally seized on his chance and did produce a paper which is titled, "Does Gravitational Radiation Exist?" And this was precisely his argument. His argument was, well, the Wheeler-Feynman absorber theory tells us how the advanced potential is broken down and you end up with just the retarded solution. He says, but we know that gravitational waves have very weak interaction with matter, so perhaps in the gravitational case, this reaction is insufficient for the back reaction of the multitude of sources out of the universe to break down the advanced potential. So in the specific case of gravitation, a binary star system would not, in fact, transmit energy because the advanced part of the solution is broken down. So here's Rosen. So I mentioned here, I guess, I've already sort of said it, that Infeld and Rosen kind of carried on what we might call this tradition of skepticism. Although we must again be careful. And Infeld likes to give everyone the impression that Einstein shared Infeld's views on this. Although I think a more objective reading of Einstein's last statement on the subject in 1936 sort of suggests that while he thought this was an interesting question, he did feel ultimately that in fact the binary stars would be expected to emit gravitational waves. Let me briefly mention that in 1955, Rosen already tried to show that perhaps on the basis of the invariance, non-invariance of the pseudotensor, that gravitational waves wouldn't be expected to carry energy. The person who, I don't have a picture of Perani, but he's a very well-known author of children's books. So the person who really answered that was Felix Perani, who at the suggestion of John Singh decided to apply the equation of GDC-GDation to the motion of, to the topic of gravitational waves. And Perani then presented this at the 1957 Chapel Hill conference, and both Richard Feynman and Herman Bondi picked up on this and produced what is sometimes called the sticky E argument. A nice argument which says, well, if you do move things around, you can certainly make clear arguments arguments that that should, in principle, produce energy that's absorbed by the things that you're moving around, and therefore the waves must carry energy at some time. And I have a picture here of Feynman talking with Dirac at the later 1962 conference in Warsaw, which, judging from his letter home, Feynman was not very happy to find that there was still considerable debate on the subject 5 years later, and he referred to the fact that there were 128 dopes at the conference, even though, in fact, the registered participants in the conference were somewhat less than 128. So maybe some freelance dopes have turned up to attend the meeting. The person who took Einstein's views, or musings, maybe rather than views, on Ritzenscheidt-Rode most seriously was Infeld, and he really propagated in the post-war period from 1950 on this idea that maybe binary stars shouldn't really radiate gravitational waves. And this led to the idea that, okay, maybe we can answer this question with the problem of motion, right? So maybe we can look at the actual system and see if there is damping, and that is what answered this debate which has arisen. So it certainly had a healthy aspect. I guess Thibault alluded to the fact that there are many other things you might think of doing rather than doing calculations beyond leading close to Newtonian order, and here was one reason that encouraged people to start doing it. Let me give you a little idea, though, of the difficulties that were encountered earlier on. The trouble was that people kept doing the calculation and they kept disagreeing on the result. And as a matter of fact, not always getting the right sign, right? Not always getting that the source was damped. Early on, you had Hooney in 1947, who got the wrong sign, anti-damping. Infeld and Scheidegger in 1951 argued for no damping at all. So, their work was answered by Josh Goldberg, who showed that while Infeld and Scheidegger were trying to show that certain terms would disappear if you did a coordinate transformation, Goldberg showed carefully that these effects would simply appear in other terms. And then we have Fock getting a result that agrees with the quadrupole formula. Perez getting initially anti-damping, but then doing careful matching, getting a sign that agrees with the quadrupole formula. And Smith and Havas using a fast motion or post-Minkowski approach, getting the wrong sign. And only really in the 1970s, and so I left this out, but do you start to get more people agreeing more often. And I think Thibault already talked a little bit about the post-Newtonian versus post-Minkowskian approach, slow motion versus fast motion. And I think I'll just skip on to here. Thibault also talked about the use of max asymptotic expansions. I'm going to talk about them briefly just to say this was one way in which a means was found of more easily reconciling the different kind of calculations. One of the difficulties with the calculations that I mentioned earlier was it's all very well to talk about what's the right boundary conditions. Right? This idea of do you have an outgoing system of waves or an ingoing system of waves is really just talking about your boundary conditions. But in a way, it was futile to talk about boundary conditions because nobody had a very good idea how to correctly apply those boundary conditions to the source system. The boundary conditions were applied in the very far field asymptotic region, and it wasn't very clear or unambiguous how they then got applied to the actual source system. And so it seems as if some of those results that got anti-damping simply got them because somebody was applying a different boundary condition from the one that they imagined that they were actually using. And so one benefit of introducing the matched asymptotic expansions was that it provided a better, more clarifying way of actually doing this. Thibault reminds me, though, that the early work on matched asymptotic expansions itself was criticized later on, and this, of course, points out, after all, one of the difficulties that skeptics had, right? So if you can find that Bill Burke's work has some errors in it, there's always that danger that if the quadrupole formula is, you're trying to answer the question, is the quadrupole formula the right answer by doing a calculation, there's always that temptation to stop when you've got the result that agrees with the quadrupole formula. So this is what you could call the theoretician's regress, right? When you're doing research and you're trying to answer a question for the first time, technically you're not allowed to decide, this was the right answer, so I can stop at this point. But it's very, very difficult to know when to stop because, of course, there's always the likelihood that there are some more errors that you have to cover. So this was genuine difficulty that people encountered. Here's a list of a few of the objections. There's no time to go into a great deal into one animated with skeptics, but I'll be happy to talk to anybody afterwards. We talked about Rosen saying that gravitational waves cannot transmit energy, answered by, I suppose, at some level, the Bondi-Feynman thought experiment, that binary stars don't radiate because they are freely falling systems. That was a very big argument that was put forward. Allegedly, Bondi asked a room full of relativists, if I hold one ball in my hand and I drop the other one, which one radiates gravitational waves? And Ted Newman claims that that was about a 50-50 response in the 1950s. And so that was one reason for doing the probable motion, so we can say that was answered in that way. And then, of course, I'll skip ahead to the bottom since we're running out of time, but binary stars may radiate, but then the question becomes, does the quadrupole formula actually apply? Even if you feel like you've decided that it is damping and so on, the next question is, what is the precise solution? And these questions were really coming to the fore when you finally had the binary pulsar data. So now you actually have some observational data, and as Thibault says, you have not just the question of the abstract idea of infinity and what the gravitational waves are reaching infinity, but what gravitational waves are reaching us here on Earth. So when Joe Taylor and Russell Hulse discovered the binary pulsar in late '74, this didn't start the quadrupole formula controversy. If we can divide the era into two sections, first of all, we had this debate of whether you get damping at all and what the sign is. From about 1970 on, the controversy is usually referred to as the quadrupole formula controversy because it's settled into, okay, maybe we're convinced that there's damping, but the question is, does it agree with the quadrupole formula? You can argue that it wasn't so much that the numerical data settled the question. In ways, it just added fuel to the fire. It made it a more important question, right? Obviously, it's all very well to say, Taylor himself has said that when the first he was aware that there was skepticism about the quadrupole formula, even though he had obviously spoken to theorists up to that point, was when he went to a conference and one of the skeptics asked him a question afterwards. So there was an interesting, at least initially, sort of a little bit of a language barrier between the experimentalists and the theorists. The language barrier, one way of addressing that, of course, is to provide what I guess Peter Gallison would call a sort of a pigeon, a way of translating between the theorists and the experimentalists. And an example of this is the parameterized post-Newtonian approximation. Because, of course, the difficulty in theory testing is it's not, to paraphrase the National Rifle Association, it's not theorists, it's not theories that make predictions, it's theorists that make predictions. You can have a theory. You can have a theory, but somebody has to do the calculation to find out what the prediction is. And it's a little unfair to expect the poor experimentalists to have to do it for them. So the idea of the parameterized post-Newtonian approximation scheme is that if the theorist does a certain amount of work and identifies his parameters, then the experimentalist has a relatively easier job to identify. Nevertheless, one thing that I want to, I think I'll skip ahead, yes, here's a nice picture of Thibault. One thing that I do want to stress is that while it's easy from the historical side to say, well, there are these language difficulties, at the same time, I think what physicists experience is that often there is a shared language in physics. And so ultimately, a key feature of the resolution of the debate is the very close work between Thibault and Joe Taylor from the theoretical and the experimental side to show that there was ultimately a very nice match between the calculations and the measurements. And an interesting aspect of this, and Thibault may comment on his feelings about this, is that eventually, for a while, there was a certain disagreement between the theory and the experiment. And it turned out that one of the reasons for this was the fact that the binary pulsar system is in a different part of the galaxy, so it's in a different accelerating frame with respect to us. And an interesting way to turn it around, which is done in a paper by Thibault and yes, that's right, Joe Taylor, I got that wrong. Adding it in at the last minute. Thibault kindly provided me the reference, I'm going to mess it up. Thibault, Demore and Taylor, 1991. They show if you assume the quadrupole formula is correct, then you can use this to give you information about the structure of the galaxy and the distance to the center of the galaxy. And I got the impression from talking to Joe Taylor that he felt a little disappointed that because the quadrupole formula didn't quite have the epistemological underpinning that would have been desired, this could have easily been one of the very first good measurements of the distance of the center of the galaxy, and he felt maybe it didn't quite get what it deserved, the recognition it deserved, because of the epistemological situation on the theoretical side. And then I put this up, and I forget how much time. Oh, no, it's okay. So I put this slide up in the hopes of commenting that the Lisa Pathfinder mission was well on its way, but I guess the launch is delayed. But also LIGO is happening. So, I want to stress the importance of the sociological issues, because after all, if you're going to put a lot of money into detecting gravitational waves, it's obviously necessary that people feel that the problem is well understood and that the gravitational waves do exist and do transmit energy. At the same time, when one does look at this sort of sociological side of things, there's a difference in the way that the historians talk about it and the way the physicists talk about it. Physicists, like Feynman, I think, would say here, like to say, well, the problem is really one of getting the right people to work on the field. But, that's not very different from the problem that we mentioned a minute ago with the theoreticians. Right? How do you define the right people? The right people are the ones who got the right answers with their calculations. But we just said, well, we should be careful about assuming that you have the right answer to your calculation. How you get the right people and exclude the dopes is clearly an interesting sociological question. And hopefully in the next slide, or maybe I didn't, I'll advertise Jürgen Rehn and others in his group will talk during the historical part of the conference on an important aspect of this, which is if you feel that sociology is somehow interesting, you have to pay attention to the building up of the disciplinary structures. And that's something that I think plays a very, very interesting role in this history, but there isn't time to talk about it today, but it will be spoken about later in the history part of the conference. So I'm going to quote, to make that point, William Blake, improvement makes straight roads, but the crooked roads without improvement are roads of genius. So this is one of his proverbs of hell. And Jürgen Ehlers once commented that physicists are a bit like an advancing army pursuing a scorched earth strategy. They burn everything behind them, and they don't like to look back. And from a pedagogical point of view, it is natural to want to draw a reasonably straight line between the original question and the eventual answer. But typically, the advancing army did not follow that straight line. They had a much more crooked path. And so from the historical point of view, it's very interesting to look at the actual path that was taken to try to figure out what happened and what were the necessary steps, or maybe even some of the steps that were unnecessary. And another proverb of hell, since I'm a fan of Blake, I was delighted to discover one time a few years ago that John Wheeler also is a fan of Blake, and he includes a nice proverb of hell at the very back of MTW. What is now proved was once only imagined. This comes out nicely, actually, in Feynman's remarks at the Chapel Hill Conference in 1957. He said, well, the trouble in this field is that you don't have any experiments yet. Well, that's okay. You have to calculate anyway. You have some ideas about the way things go on, and you should still push forward. And maybe contradictions will occur, and that will tell you that you're on the wrong path. But nevertheless, you shouldn't be completely deterred, because there aren't yet the experiments. And so the ideas that were imagined originally by Einstein back in 1916, if they aren't entirely proved, if the problems are only more or less solved, which I think is also a good quote from the class, nevertheless, we have in fact come a long way and know a great deal more, at least about what we don't know, than Einstein did in 1960. So I'll leave it there. Thank you very much.
Thank you very much, Dan. I think now we'll ask Thibaut to come back and join us, and we have set aside half an hour for questions and discussion on this entire issue. I'd just like to ask, can we get another microphone for Thibaut? I have a question. Okay. And good. Let's.
Okay, I think one should mention that Einstein's Waterpol formula was a factor 2 too small, and the error was discovered by Edding in 22, so he corrected the Waterpol formula. Usually nobody's mentioning that this was not fully correct, the factor 2 too small. Another comment, that the calculation by work related to the calculation shown in Mrs. Formula in the book, that it was not correct, was already in 1980 discovered by Walker and Will. And in the Lesouche proceedings, Kim Thorne was saying that, I'm sorry, I did an error. My previous calculation, 69, was an Edge-Wheeler gauge, then I did a calculation harmonic gauge, and the transformation and error. So Mr. Thorne-Wheeler result in the book is correct, but the derivation has some flaws. Maybe another comment to the gravitational existence of gravitational waves. Usually Daniel Lifshitz is forgotten to be mentioned because Daniel Lifshitz's book is not popular in the US, so that was not, at least in the past. And Daniel Lifshitz in 41, derived in Russian, the Russian edition was in 41, the first edition, the English was in 51, they derived the quadrupole formula for self-gravitating systems. And there was no doubt for them that gravitational waves do exist. But this book was never taken as reference in discussing the question about the existence of gravitational waves. Okay, maybe later I will also give other comments.
Yeah, thank you very much. I find myself with many questions, but I guess I can't ask most of them. One thing is that when we hear about errors that are made, people are not mentioning the nature of the errors. Is that because they're just totally stupid errors, like Einstein dropped a factor of 2? Or is there a physically interesting way that he made that factor of 2 error? Another question would be on the Einstein-Rosen paper. What sort of an error was it? I think I'd like to hear a little bit about that.
Sure, yeah, I'm delighted. I didn't close in very much on the errors just because there were so many different varieties not just with Einstein, but over the whole history. For instance, we just heard one common enough source of error is you weren't quite sure what coordinate system you were in, or two people did a different calculation, but what they thought was the same calculation, but a different coordinate system. I think there are definitely some cases in the history where people thought they were in disagreement, but it turned out that they agreed, but they were just working in different coordinate systems. Specifically, in the case of Einstein, the factor of 2 error in the quadrupole formula, which you so correctly pointed out, was more in the nature of a numerical slip. But for instance, that paper in itself, published in 1918, was a complete rewrite of a paper that he published, his first paper on gravitational waves in 1916, where he introduced the pseudotensor, and of course it's non-invariant, but in addition to that, he got his calculation of, he constructed the pseudotensor wrongly. So if you know, when you do the linearized approximation, you have your little h mu's, and then later you introduce h mu prime set of functions, and he put the wrong one of those into his pseudotensor. So he put the wrong set of quantities in, mistaking his primes for his unprimed quantities. And so he had a completely wrong pseudotensor. And that gave him all sorts of, he didn't get anything like the quadrupole formula the first time he tried it. So usually in 1918, when you're kind of looking through his history, you're so relieved that he basically got the right answer that you kind of forgive him a much more simple slip that it has a factor of 2 wrong in it.
I will ask a stupid question. What is the definition of energy and what is a wave?
Yeah, that's a difficult one to answer. Obviously, especially in the case of gravitational waves, it is a bit like that question. You're swimming in the ocean, and which part is the wave and which part is the ocean?
Along Yvonne's line, I would point out that there's also a mathematical aspect of this problem. And I think it was around 1930 or so, Stellmacher realized that Einstein's equation have characteristics, null hypersurfaces. And once it was found out that the equations are hyperbolic, it's on the mathematical side, it's just obvious that they have to be bases. This is one remark. The second remark I would like to make is the following. We talk about ion resistance. We always think mainly about the matter. But radiation also takes an important part. Therefore, if we set up data for this problem, there should also be solution of the equations where a big gravitational wave comes in and takes the system apart. Therefore, it's very important to find the right data which determine the solutions we expect to see usually.
By the way, just to comment on this, you were on one of on transparencies we are seeing is, I would say, the numerical data, for instance, they try to be close to what you want, but they are not data that will have no radiation. So they have some incoming radiation called junk, I think, but they are close enough, and then you see that this junk radiation goes away. But in one of the graphs, you could see that when it goes away, then it goes to the part which is the pure conservative thing. So everything seems to be okay.
I wanted to follow up on the question that Ted asked. You started, Danny, your talk by giving the story about Einstein, this paper which was withdrawn. What was the mistake? And then you said Intel did the calculation on Blackboard, and Robertson said, what was that mistake?
Yes, thank you, Chris. That's a great question. So the argument that they made was there's a singularity somewhere in our metric, and this singularity it validates our metric representing what they were looking for was plane gravitation. And after the war, it was shown by Robinson, and somebody else, that, of course, this singularity was in fact only 40. So they needn't worry about it at all anyway. What Robertson said was, well, if you're so worried about this singularity, why don't we just change the symmetry? And instead of talking about plane gravitational waves, we'll talk about cylindrical gravitational waves, and then your singularity can be hidden away at the central axis, and we can think of it as a source. In a way, as was shown later, they didn't even have to do that much because, in fact, so this is another issue that came up several times in debate. Do you understand the difference between a quark and singularity? It's difficult to know because, unfortunately, in Infeld's autobiography, which is what I'm relying upon for the source of my anecdote, he doesn't tell us what Robertson said. I'm guessing, though, that it probably was something along the effect of if we switch it around to the coordinate system, because that's what Einstein thanks him for in the data report. And the referee's report also says, towards the end of the referee's report, it says, perhaps what we're dealing with here is really cylindrical. Actually, the referee is quite, he knocks on the door, and he does in fact say, he wonders about, are we really dealing with a physical singularity? So I think if Robertson had had the opportunity to sit down with Einstein and confess, which he obviously never did. By the way, I was the referee, and maybe we should go over this. I think he decided that would be the wrong approach. As we saw from that letter, Einstein was maybe not very happy with the referee. So in the end, I think he decided on this very indirect method. And so it looks from the going more by the little acknowledgement in the eventual published version of the paper that he just sort of confined himself with saying, well, I think you could obviate all these problems by just switching to the cylindrical.
But think, just a moment. The basic point of Einstein was correct. I mean, he had a deep issue in mind. If you have a solution of the linearized equations for a nonlinear system, you are never sure there exists exact solution with linearized approximations. This is a deep problem, and there are nonlinear PDEs where it is wrong. Okay? So he was right in asking it. Today in textbooks you say, okay, linearized gravity, therefore waves exist. No. Okay. So that was a complicated question. So, yeah, and we know in some cases. So Einstein was asking a deep question, as often.
Yes. So we know that if you try to construct a vector theory of gravity, the gravitational waves carry away negative energy. I was wondering if anyone knew who was the first person to notice that.
Vector theory, you mean?
Like Maxwell.
This is Lorentz. Lorentz in 1900 used Maxwell equation and said there are positive negative charges and they don't exactly compensate, and then so he changed the sign. He used vector theory with F nu square with the wrong sign.
But was he thinking of gravity? Because you said
yes,
gravity. Poincaré in 1905, you said, was the first one to mention gravitational waves.
Yes.
So Lorentz was 1900.
Yes.
So he wasn't thinking of this as a theory of gravity?
Was, I mean, they were relativistic. They were, action at a distance. Theories for gravity all over the 19th century. Okay? Lorentz was one of the last of this thing. Except he computed the period of precession, for instance. Then, which was like a standard thing that people would do and did not find the correct answer. But in this thing, there was the wrong sign for it.
Laplace also talked about gravitational waves, didn't he? Didn't he?
No, let me repeat what I said. Laplace was really talking, saying, why, if the action at a distance is not instantaneous,
That's right.
but what essentially he was doing, actually he was doing something more subtle. He was saying that, like in Le Sage theory, the force does not come from the companion to the thing, the field comes from infinity. He was speaking about advanced waves, okay? Coming, concentrating towards the companion and passing through the object we are interested in. And then he was saying if this propagates with a certain velocity, there will be a time delay and an aberration effect because you move. So he computed this and he got the first order in V over C effect with the right sign because he was using advanced waves. Now he was getting damping, otherwise he would get anti-damping. Then he put a limit of 7 million times the velocity of light by putting this in the motion group and using data.
A couple of brief comments. You mentioned Bondi and the internal structure. He was talking about the difference between gravitational reduction and gravitational radiation. He talked about Tweedledum and Tweedledee, for those who remember that. The second point is the outgoing radiation condition. I remember Troutman as being the person who really made a thing about that, and that then went on to Bondi, Vandenberg, and Metzner. The third point is that Pirani, he made this huge contribution with the GDC deviation equation, but what hasn't been mentioned here is he then concentrated on the Weyl tensor as the thing which really carries gravitational radiation rather than the metric tensor in a certain sense, and that leads to the idea of the Bell-Robinson tensor as being the energy momentum tensor rather than any other. And so my final comment is that there was a lot of work there on the energy, conveying energy by gravitational radiation. What we haven't heard is about the entropy associated with gravitational radiation. And I think that could be a very interesting subject for discussion.
Anyone want to comment on that while we're moving on? Question? Entropy. I don't know if I have very much intelligence, but it is an interesting.
We should check, by the way, the work of Louis Bell, was it not before? I mean, in France, the fact that this was the Riemann tensor, the Weyl tensor, which was important, was known and discussed in papers by Schnorowitz and Yvonne before Pirani. We should check that.
Question, I think.
Yeah, thank you both for very beautiful presentations. Just a quick comment on the Einstein refereeing situation. Dan, I always love that great letter you show. But maybe it's worth reminding ourselves that Einstein might have had good reason to be surprised that this was sent out for refereeing. Because at the time, this was not standard procedure at the Physical Review or in most physics journals in the US or in Europe. And so Einstein might have had reason to be surprised that the paper he sent in for publication was actually diverted. The PhysRev only began requiring peer review for every submission 20 years later. And even then, the referee reports were often 3 or 4 sentences. They were very rarely 10 pages. So it's actually quite surprising the way that whole thing played out, to have sent it out for referee at all, have a very extensive and very detailed referee report. And so we might all want to have the same response to editors today, but today we won't get away with it. 1935, 36, one might have thought we could have a different situation. Just a comment, otherwise a lovely presentation.
Yes, thank you, David. In fact, the first 2 papers he submitted to this review we now know were not sent out to a review. We don't know the reason given, but we can only conclude that Jacques Tate, who was then the editor, was a shrewd man who said, Einstein, Podolsky, Rosen, controversial but important. Einstein, Rosen bridge, interesting idea. Gravitational waves don't exist. I'm really dubious. I think I'm going to send it out.
By the way, speaking of referee reports, I remember that the paper of Arnold Rosenblum, who is not with us anymore, controversial paper that triggered the incredible controversy. I mean, everybody knew by looking at the paper that it was wrong. But I remember, I forgot whether I discussed with the editor or not, the PRL editors decided that probably it was wrong, but it would be good to stir the community. So maybe PhysRev could have done the same thing, because it would have been more interesting to have a wrong paper of Einstein, maybe.
So could we still today use Poincaré's description of gravitational waves and its generation, which is based on just special relativity combining with gravitation?
So the question
could we use Poincaré's description of gravitational waves today to convince us of?
Okay, Poincaré introduced the word on gravific. What he had in mind, I mean, he wrote general models of interaction at distance compatible with Poincaré-Lorentz invariance. So he wrote all the invariant way of writing the two-body force generalizes Newton's law with either retarded or also instantaneous and things like that. And he knew from the work of Langevin in particular about the emission from electromagnetic systems, and he commented that in 1908, that probably there would be a wave associated. So here it was not a field theory, okay? It was an action at a distance, but Poincaré was sharp, so he knew if you write the field theory, there would be waves emitted, if there is a wave at infinity that will act on the system, and then the main effect would be P dot. That's a separate 1908 paper of Poincaré where he says there would be an effect of the circular acceleration of the orbital motion.
I wanted to come back to Ted's question about interesting mistakes in history, possibly mistakes that end up being more fruitful than if they had not been made. It connects the topic Einstein's work on gravitation and radiation in the 30s to his work on the problem of motion in the 20s. So, as Dan said, right, in Einstein's first work on gravitational waves, it was all in the linear approximation, and that, his opinion on that didn't change. In the linear approximation, you do have gravitational waves. In the 30s, he asked himself, well, but how much does that really tell us about the full nonlinear theory, that they exist in the linear approximation doesn't mean they exist as a strict solution. And something similar happened in the 1920s, leading up to his work on the problem of motion with Einstein and Comma. And we only know this since recently through work on volume 15 of Einstein's collected papers, which, in the context of which we discovered his correspondence with Yuri Leinich, who was later rediscovered by Wheeler and Wiese. And there we see that Einstein was convinced at the time, and he writes that to Leinich, that one should not treat matter in the context of general relativity, even of vacuum general relativity, by singularities, because he was convinced that if you did that, then you would allow for a solution where you have two singularities, or two gravitating bodies represented by singularities that would be addressed with one another, with respect to one another. So, well, that is empirically inadequate. Two gravitating bodies have to approach each other. And then Leinich said, well, that is a feature of the linear approximation of the theory. If you have two one-particle solutions, then you will have a superposition of two-particle solutions, and those would also be addressed. But we don't have any indication that such a solution would also exist in the nonlinear theory. And then Einstein comes back to Leinich and says, well, we know there is such a solution. Weyl and Bach discovered it in the 1920s. A strict two-particle solution to the full field equation. And then Leinich comes back and says, no, we're really not sure that this really, that there is such a solution. And then Einstein must have come back to these papers by Bach and Weyl, that's the symmetric Weyl solutions. And in the end, repurposed them, reinterpreted them, and said, well, this actually is not an admissible solution because it's not a superposition of two one-particle solutions. It's more complicated because it has a singularity along the z-axis. And that, in that context, we also find out that Einstein is very happy to admit singularities as representatives of material particles, but not singularities in the free field, so to speak, in the non-material part of space-time. And then that whole, comparing solutions in the linear approximation and starting to be more skeptical about whether linear solutions correspond to full solutions of the field equations, then that kicks off his work on the problem of motion with Einstein and Comma, where he then asks, so if the nonlinear regime is so different from the linear one, then we can now really ask whether the equations of motion for a particle subject to an external gravitational field are uniquely determined by the vacuum field equations. So in that correspondence, we really see in realization that he had made a mistake, and that kicks off his whole new work on the problem of motion in the 1920s.
For those of you who are dense, we'll talk more about this.
Just a quick point of clarification about the mention of the vial tensor. I mean, it wasn't so much the vial tensor as the application of the Petrov classification.